Ladies and gentlemen, welcome back to your favorite class. How's the volume? Can everyone hear me okay? I don't lecture from my office very often virtually. Usually it's from home, so appreciate the thumbs up there, Jordan, helping me on my way. That's nice. Glad you're all here. You made it for the Thursday lab section. So just right off the bat, I'll tell you there's no real assignment for lab this week. All we're going to be doing is kind of having a series of lectures. And as I sort of said in the lecture yesterday, the lab period will be variable from week to week. Okay. This week we're just going to have some lectures and some talking by me about how to write a good technical report, because that's what you're going to be doing for a lot of the labs that'll take place this particular quarter. Okay. Other events that'll happen during this lab, obviously, we're going to have a quote-unquote lab where I send you a video of the experiment that has been recorded, and then you take the measurements that you see in the video and write your lab report with that experimental information. Right? So that's going to be kind of how the lab section works for this class, and I'm going to be kind of pretty hard stickler about writing this quarter. So you might have gotten away with some, let's say, relaxed lab report writing in previous classes, maybe physics classes, chemistry classes, etc. But this time, I'm bringing the pain, okay? So get ready to write and write well, and I'll help you along the way, all right? So with that idea in mind of, writing good lab reports and good writing technical reports, I want to spend time today talking about, one, why it's important to communicate effectively, right? So just generally this idea of being scientifically literate and having good vocabulary and communicating well, why that's important, and what happens when you don't communicate well and how it can be hilarious. And secondly, I want to go through a slide deck that really details what I'll expect from your lab reports, and sort of a set of notes that you might want to revisit as you're starting to write your own reports. Okay, so the first thing that we'll do, and the first thing I want to do to motivate this lecture, is talk about some funny stories of people being scientifically illiterate and why these things are bad and why people don't understand sort of the scientific process and how that can lead to bad things. So I'm going to pull up some PowerPoint slides here and share them with you guys. These slides are available on Blackboard if you'd like to follow along on your own. Otherwise, I'll project them here in Teams if you'd like to follow along with me. Just give me a second here to pull them up. Okay, and I will share my screen. So we should all be able to see the screen now, showing the PowerPoint slides. Okay, so I'm going to talk about scientific literacy. Some of this material I stole from Neil. He's like this amazing astrophysicist. If you've never heard of him or never seen him, you should go on YouTube and just like spend an afternoon watching Neil deGrasse Tyson's lectures. He's hilarious and amazing, all the things. Okay, so I want. There was. There's these, and they're like identified flying object. So usually when people hear unidentified flying object, they immediately go to aliens or something else, right? And my point of discussing this is be careful about drawing incomplete information. So you're looking up at the sky, you see this bright light, and you're looking at it and you're like, oh my gosh, this bright light is an unidentified object in the sky. It must be alien. Okay, like how did you come up with that conclusion? You don't have enough information to make that conclusion. And this sort of thing happens all the time, and it's very dangerous in the scientific world for people to make conclusions with information. And it will be dangerous for you when you're doing your lab reports to conclude certain things with incomplete information, right? So this is kind of the point I'm trying to drive home here. So to the credit for the people in the video, they were pretty good about saying it's this bright light, we don't know what it is it a missile, is it blah blah blah. Okay, so there's an article that came out the next day about what was going on with that light, and these people are talking about, I see this bright light in the sky, it must be an alien. Okay, well, the Washington Post just kind of said, a mysterious light that rocketed across the sky, sparking fears of nuclear war, an incoming meteor, and an alien invasion. was actually an unarmed missile. All right, it's a test fire by a Navy submarine. Okay, so you just have to get more information to finally come up with a conclusion. People were concluding it must be aliens, like it must be nuclear war, like run to the hills and get in your shelter, rawr, okay? Like how did you come up with that? You don't know that, right? Like it sounds silly, but this happens all the time. It's much subtle. You sometimes don't have lived in a few start. I won't start it key. Tried to start. No, I tried to. If I jump to the that it must be the battery and it's not the battery, well, maybe I wasted a lot of time going to the car parts store and getting a new battery and installing it in my car and then turning the car on again only for it to because it was the alternator or something else, that was the problem, right? So you need to make sure that you have enough information to conclude that. So get out your ohm meter, get out your voltmeter, put it on the battery, and make sure that that really is the issue before you spend more time or conclude for sure that the battery is the problem. Okay? So it's a common occurrence. Another possible issue of jumping to conclusions with incomplete information. I don't feel well. It must have been that Chinese food. Like people say this all the time. It's like, how do you know that? You're gonna blame this restaurant. There, you got your Chinese food. You have no idea if it was that Chinese food. Did you like pick out a little bit of your like stomach and take look at the chicken under a microscope and it had higher levels of E. coli? Like you don't know that. Okay, you might just like have the flu or something. Like you don't know. And so you're blaming this restaurant. Maybe you write a bad review for them for like you don't know for sure that it was their problem, right? You're drawing conclusions from incomplete information. So be wary of that. This old outfit I found in my closet will make me look great. Probably the reason it's in the back of your closet. All right, you might need more experimentation. Put that thing on. Maybe you discover there's a big hole in it. Okay, you need more experimentation to discover if it actually will, look as good as you remember. Maybe that old vest from 1972 with the sequence on it is the reason it's in the back of the closet. All right, at least that's why mine's in the back of my closet. Okay. I did this the other day. To light my refrigerator out, the fridge must be dead. Well, no, the light bulb was just burned out. All right. So again, if you're calling the repairman to repair your fridge and he walks in your house and says, "No, it's just the light bulb's burned out," you're just gonna look like an idiot, right? So make sure you're not jumping to conclusions with incomplete information. So people are generally uncomfortable, steeped in ignorance. What I mean by that is something is not working correctly, and you sort of assume some conclusion to help you feel more comfortable about the situation. Okay? It's like there's this bright light in the sky. I just I can't accept the fact that I don't know what it is. I have to make something up for it being there. Okay, it's got to be aliens. It's got to be a nuclear thing. It's got like no, unidentified flying object, okay? You don't know what it is. So don't jump to conclusions, okay? Just understand maybe more experiments are required. Okay? You have to be certain through your experimentation that you have enough experiments and data to conclude what you're going to conclude. Just to say off the cuff, my battery is dead. I need to go buy a new battery. Okay, well, test it first and make sure. You need another experiment, etc. All right. Okay, continuing with my sort of expounding here on some funny things. These are stolen from Neil deGrasse Tyson, and he's amazing. All right, things you've probably heard in your life. What goes up must come down. The sun is yellow, orange, red, whatever. Astronauts are weightless. The North Star is the brightest star. Days get longer in the summer, shorter in the winter. At noon, the sun is directly overhead. Sun rises in the east, sets in the west, and solar eclipses are rare. Okay. All of these things are not true. Okay. A lot of you, I'm sure, look at these things, and at least some of them you think are true. And this is a problem about vocabulary and definition and taking colloquialisms at their face value without really thinking about them. So let's talk about this. All right, what goes up must come down. Okay, well, no. We have satellites that have escaped our solar system. There's, a velocity at which you can shoot things from the surface of the Earth, where the Earth no longer has a large influence on how they behave, right? So those those satellites, they ain't coming down. Down being, towards the center of the Earth. All right. The sun is yellow, orange, red. No, the sun emits white light. That's why when the sun shines on things, it reflects all possible colors of the spectrum, right? So sometimes when the sun's coming in on the horizon, because of the atmosphere and the blue light's being reflected off, it appears red, orange, and yellow. But no, the sun is emitting white light, right? Astronauts are weightless? No. What is keeping them in orbit? They still have a gravitational attraction to other objects, right? So there's still this G m1 m2 over r squared that exists as this gravitational force between the astronauts and the Earth, and between each other, right? So they are not weightless. They just appear that way because everything around them is moving at the same relative velocity. So it sort of looks like they have no weight. Okay. Days get longer in the summer, shorter in the winter. This is like commonly thrown around, but just not true. Okay. The longest day of the year, and by longest we mean the most sunlight. So aside from the fact that a day doesn't change in duration, let's just talk about the amount of sunlight that might happen to be in a day. The longest day of the year is June 20th, 21st ish. All right, the summer solstice. That is also the first day of summer. Okay. So if the first day of summer has the most light, that means that every other day in summer has to have less light than that. All right. Same thing in the winter. The shortest day of the year is the first day of winter. So every day in winter, you're getting more and more and more light. So this statement just is not true, but people say it all the time. Okay, just to be very particular and very careful about your vocabulary. All right. At noon, the sun is directly overhead. Okay. If you're not between the Tropic of Cancer and the Tropic of Capricorn, this will never be true. Okay. For people in the northern hemisphere, the sun will be slightly tilted to the south when you're looking at noon. And if you're in the southern hemisphere, the sun will be slightly tilted to the north. It won't be directly overhead. All right. So it's not right overhead. It's tilted, one direction or the other, because you're not directly at the equator or near the equator. Okay. Same idea with rising in the west and setting in the east. Okay, it can't rise directly in the west and set directly in the east if you're not between the Tropic of Cancer and Tropic of Capricorn. People say this all the time, right? And I think people mean to say that it generally will rise from that general direction and generally set in that general direction. But if you're reporting this as an absolute certainty, that's not really the case. Okay, solar eclipses are rare. Well, okay, let's define rare. They happen about every 2 to 3 years. Okay, that's really not that rare. I mean, you don't say like rare Olympics or rare presidential election, which happens every 4 years, right? So really not that rare. And what's the point of this? The point of this is that colloquialisms get thrown around all the time, and people just take them for what they are a lot of times without necessarily thinking about them in great depth. And so if you're writing something or you're communicating something to someone and you just write some colloquialism off the cuff without actually checking it thoroughly, and the person who is reading what you've written understands that that's not necessarily an accurate statement, you're going to start losing credibility from the person that's reading what you've written, or the person that's listening to your presentation, or the customer that walked in the door, or whatever. And you just really don't want to lose trustworthiness and faith of your colleagues because you like speaking off the cuff some random thing that you heard with no data to back it up and no conceptual knowledge of it, right? So you just really got to be careful here. Okay. Other couple quotes that I think are funny. Math testing scores. Okay. Half the schools in the district are below average. This is some reporter reporting on this for some newspaper. Okay, so I'm reading that newspaper and I read half the schools in the district are below average. I'm taking that newspaper right to the trash. Okay, because the reporter, of course, half are below average. It's like what an average is, approximate average. Half are below average. Yeah, of course. What I think this person means to say is something like half of them are below some standard, or generally our average is below some standard, but that's not what they wrote. Okay, so this reporter with the headline says half the schools in the district are below average. You're trying to report on a mathematical deficiencies that the school has, and you don't even understand math yourself, right? So right to the trash with you. Okay, the person that wrote that article, I don't trust you anymore. And the editor that let that come out, I don't trust you anymore. So your newspaper, you're losing my confidence in my business. All right. So right to the trash with you. All right. again, this is another one and a little bit more subtle, but we'll talk about this later in the course. 80% of the airplane crash survivors had studied the location of the exit doors upon takeoff. Okay, this looks like sort of an innocuous comment, like, okay, 80% of the survivors studied the location of the exit doors. But the issue is that you don't have the full picture. You need the other side, okay? So you need to know about the people that did not study the location of the exit, okay? Maybe 100% of the people that did not study the location of the exit doors survived. Okay, so do you want to be in the 100% that survived, or do you want to be in the 80%? Right? There's no control here. There's no comparison of information. You don't know whether this statistic on its own is a good thing or a bad thing. You need some basis for comparison, and comes down to like control experiments. All right. Lastly, and probably my favorite, I've changed my views 360 degrees on that issue. All right, Mr. Congressman, everybody, stand up, rotate 360 degrees. I mean, you're staring right back at the same place. So this is, silliness. But I think that's kind of funny. Okay. This also happens at the highest levels of science. And this is kind of like the last couple things I'll discuss here is that I was reviewing a paper that my colleagues and I wrote. This is about 2 years ago now. And the title of the paper here is Improving Fracture Strength of Fused Filament Fabrication. That's 3D printing, but fancy language. Parts by thermal annealing in a printed support shell. Okay, so you see all these 3 authors here that are listed. Ryan Dunn, me, Kevin Hart, and Eric Wetzel. These are 3 people that all have advanced degrees in engineering, graduate degrees in engineering. Okay, so I'm reading kind of the paper that these people have written, and even at the highest levels, these guys, PhDs, master's degrees, they're making mistakes in their English, and it just you got to be crystal clear, because if you got a first-time reader of one of your papers and he comes across some bad English and is like, I can't follow this guy, I don't understand, you lost him. Okay, so some quotes from this. In contrast, the annealed load displacement curve. Okay, this is an object-subject sentence issue. A load displacement curve is typically some piece of information that you'll get from like testing a piece of aluminum or steel or whatever the material is. Okay, you probably did this in your material science classes. Okay. So when you're talking about an annealed load displacement curve, the load displacement curve is the subject of the sentence. So you're annealing the load displacement curve. I'm going to take this curve, this graph that I have, and I'm going to anneal it. Okay, it doesn't make any sense, right? You have to be careful with your object-subject relationship, right? You're not annealing a load displacement curve. What you mean to say is something like, the sample, the load displacement curve of the sample which was annealed, right? That's a little bit more clear. But when you're talking about a curve that was annealed, it's not very, very good English. Okay. Continuing, we got some spelling issues here. The old British spelling of chamfer. Okay, so that's a little bit strange. And then also extruded from the base at 45 degrees. All right, if you're going to make a reference to an angle, 45 degrees, you need some reference point. 45 degrees to what? The horizontal, the vertical, even though those things would generally be the same, to some other reference plane. You got to like expound on that a little bit. Okay. Also, the title here has support language, support vocabulary, right? Vocabulary is important. When you're talking about increasing the strength of a material, you're talking about increasing the amount of load a sample can hold before it fails like in tension. That's a strength metric. But what we actually did was check the toughness, which is a measurement of how well the sample can resist crack propagation, which is a completely different metric in mechanics. And so if you're talking about improving strength, but your entire paper is about toughness, the title isn't really reflective of what you've actually done. All right? So a lot of belaboring here, but I just want to drive this point home and just last comment here. What is the point of all of this stuff? Well, I've kind of mentioned this quite a bit, but the point is that if you're an engineer, you kind of have this idea that if I'm good at calculation and I, have the technical ability, that I will be successful in my job in all aspects. And it just really isn't true. As engineers, you're gonna at least have to like sell your designs to your bosses or your colleagues, etc. And so that will require communication of your design through presentations or written works or even just vocal communication, right? You have to be like a salesman. And if your presentations are sloppy with bad English, bad spelling, bad grammar, and you don't understand concepts associated with like developing good experimentation and good design, then you're going to come across as sloppy and untrustworthy, even if your designs and what you're pitching to them is actually quite good. So the communication aspect is just highly underrated in the education here, and I think for some of the reasons that I've tried to demonstrate here. So if you communicate poorly, people are going to see you as sloppy, unreliable, inaccurate, and just generally untrustworthy. So I don't want you to lose the trust of your colleagues by having spelling errors, imprecision, bad understanding of experimentation, etc. Okay, so that's it for this deck. Any questions about this? I know it was kind of a soapbox over, but soapbox moment. But hopefully, like soapbox over. Maybe we can talk a little bit more detail on what your reports should actually look like. Any questions? Peanut gallery. People awake out there. Everybody's sleeping. Okay, good. Wake up. Wake up. Okay. So let's go to the next deck. And that's going to be a little bit more specifics on how you're going to form your technical reports for this particular class. So before we get into that, I want to talk about some resources that I have available for you on Blackboard. So Blackboard, I've provided and uploaded a variety of resources that can help you on your way for your technical writing. First thing is we're going to use a common template for your lab report writing for this particular class. And so if you kind of go to Blackboard, you can see this general template that we're going to use. And everyone in 3005 is going to use this particular template. So you should be able to see it here. This is the one from 2019, but you can update with the appropriate year. So this is the ASME format template, and it would be nice if all of you did your reports in this particular format. And this will help you in organizing and keeping us all consistent and using the same particular template. So when you're writing your lab reports, please use this template. It's available on Blackboard, and you can do that. It has these variety of sections, okay? And so people often ask me, like, what material goes in each one of these sections, and what should I put in each one of these particular sections? And so I have written for you another document which contains my notes that is basically this template where I have additional information or additional notes for you. Okay, so this text here in red is text that I've written to help you sort of along your way with each one of these sections. So the abstract is meant to be a summary of everything that's to come, etc. The introduction, you want to discuss the theory behind the lab and why as an engineer it's important. The methods, what did you do? The results, strictly providing what the results were from the experiment. Discussion, interpret your results, and then conclusions and references. Okay, so when you're going to write your first reports or all your reports for this class, you can reference this if you're kind of stuck on like, oh, what goes in the abstract, I forget. Oh, what goes in the discussion, I forget, etc. Okay, so that's that. Now let's go talk about what I'm going to expect for lab reports from you guys. Okay, and this slide deck's maybe a little dense with text, but I hope that when you sit down and write your first lab report or all of your lab reports for this class, you revisit this deck and specifically this slide. Okay, so I've put this up as the very first slide because this slide to me sort of details all of the important delineations between what I would think of someone who writes at an expert level and someone who writes at sort of a novice level. And I want you guys to like be good writers at the end of this quarter. Okay, so I sort of classify people's writing into like three bins. That would be like a novice, an intermediate, and an expert. So someone who is novice is doing all of the things that you would expect sort of a novice, elementary, high school kind of writing to look like. All right, poor grammar and spelling, no attention paid to verb tense, figures and tables are inconsistent and irrelevant, difficult to follow and interpret methods and conclusions, no discussion regarding general practice and importance in relation to the rest of the world. Like just a lot of lazy writing. Okay. What I'm hoping for is you guys to at least be solid at the intermediate level by the time that you leave this class. All right. Expert level is, I'm still working on trying to get to that level. Like expert level writing is really quite difficult to do. Okay. But I'm hoping we can get to kind of this intermediate level where your grammar is good. but you might still be using some passive voice. And I'll talk about what passive voice is here in just a couple slides. And inconsistent verb tense. Good language is nice, proper vocabulary, but you might be a little bit verbose, using 3 sentences when 1 sentence might do. All right. Good basic structure, but some comments are misplaced, meaning sometimes you might write results in the discussion section or vice versa, and that can be problematic. Figures and tables well formatted, but might not be useful guides, right? So you might include a picture of your apparatus, but if you're not discussing why that particular apparatus is important, like why do you need that picture there? All right. So you got to think about, is this figure helping me achieve what I want to communicate? Right? Some general discussion of society. So how does what you done relate to the world, and why is it important for you generally? Okay, so that's sort of intermediate. I'm hoping we can get you guys to that sort of level. The expert level would be what I'm sort of striving for in my own personal life. All right, no grammatical errors, no passive voice, consistent verb tense, concise, distinct language, highly structured formatting, no additional information, all of the things. So when you're coming to write your report and you've finished your report, come revisit this slide and see if you have checked all the boxes on these sorts of things. All right, try to get yourself as close to the expert level as possible. All right, so like I said, for general formatting, we're going to use the ASME format for writing these lab reports, so that's available on Blackboard. And I've also provided that template with my own additional comments for you to look over as well if you want to take a look at that. All right. If you're citing sources, most peer-reviewed scientific journals use the IEEE format. And the IEEE format is pretty easy to understand. Maybe you did like APA or MLA in your GS 1001, 1002 series classes. I'm telling you, if you're going to write anything in the engineering world or the scientific world, you'll use IEEE or maybe ASME format, but they're more or less the same. Okay, so IEEE reference style, I'm going to pull up this document for us to take a look at quickly. This document is also available on Blackboard, and it provides all the information that you need to cite things appropriately using IEEE format. So when you're citing information in a technical lab report this quarter, what you're going to do is you're going to write some statement that someone else has proven or that you're taking from some other source, and you just put a number behind it. Okay, and you'll accumulate these numbers as you go through your writing, and at the very end you'll have a reference section which includes all of the references that are associated with the numbers inside of the writing. Okay, so end of the line from my research, number 13. Okay, so if I scroll to the end of your document in the reference tab, number 13 should have some very specific reference with some very specific formatting. Okay, if you have multiple references for one particular point, you can separate them with commas inside of the square brackets. All right, so that's how you would incorporate the numbers into the document itself, and then at the back end of this PDF file, you'll see how the references should look for each particular reference that you might use. So let's say you're citing a journal article, or let's say you're citing an ebook. Well, here's an example of how you would properly cite the ebook. All right, here's how you would properly cite a journal article. Okay, at the end of your report, etc. Okay, so a lot of different styles here, a lot of different resources and showing you how to reference them properly using IEEE format. All right, so that's that. Also in Blackboard, it's a peer-reviewed scientific article that I wrote, which follows the ASME structure and uses IEEE citation formatting. You can use that if you'd like to take a look. And additionally, Dr. Rizza has provided guidelines for writing, which are much more in-depth than what I've given in my little template. So Dr. Rizza came up with this document here, which is also available on Blackboard, that goes into a lot more depth on what each one of the individual sections should have and how you can communicate effectively and write your report well. Okay, so all the resources here available to you to write a good lab report, as much as I can give you without overwhelming you. Do we not use quotes from those ebooks in the report? I'm not quite sure I follow the question. Quotes from those ebooks. I'm not sure what you mean, Alan. Can you specify a little bit more? In the meantime, I'll continue. So let's talk a little bit more detail about the various specific pieces of information and how they'll be formatted. Figures are important. They will be an important part of your lab reports. So here's how a nice figure will look inside of your lab report. Figures are pictures, schematics, illustrations, etc. Something that you put into your document to help you explain something that might not be easy to explain with words. All right. Captions below the figure. If you have an image, you should have a scale bar. If you're making a graph, you got to put axes on your graphs. All right. You got to label those axes. All the things you've been taught since you were in high school. Like label your axis. Rawr. Okay. If you have multiple images in one figure, label each one of the individual images with a particular slide. So these are figures from a paper that I wrote, and you can see two different figures here, figure 5 and figure 6. And what these figures are is I'm doing a tensile test of a dog bone, one that's been 3D printed, which is the figure on the right, and one that has not been 3D printed, that's the figure on the left. All right. So what you see here is a series of images. The image has a scale bar. The images are very clear. You understand what's going on in the picture. Each image has its own alphanumeric character, A through F, and I detail at the bottom of the figure exactly what you're looking at when you're looking at the figure. Okay? Tensile testing of additively manufactured specimens made from reclaimed ME pouch material. There you go. That's in contrast to what's on the right-hand side there, which is sort of the native material itself. Okay, so very clear what's going on in the figure. Things are labeled. Axes look good. X-axis, Y-axis both labeled. Individual things on the load displacement curve are pointed out. So this is like a very nice series of figures. Okay, tables are a little bit different, and that it's kind of like an Excel style data dump, I guess you could say. It should be easy for the reader to follow the information. For tables, you want your caption at the top. So you see the caption at the top here. This is an example from a paper that I wrote. Specifications for samples examined during Raman spectroscopy. Okay, and then here's all the information. Should have headings for each one of the columns. There should be appropriate units where applicable, so on and so forth. Okay. Finally, when you're using the word table and figure in your writing, they should be capitalized in the writing. So if you write something like the results of tensile testing are depicted in table 4, table should be capitalized. All right. Equations. You'll be using a lot of equations in your lab reports to describe like how you calculated stress, for instance. Okay, so you're going to need to know how to format equations properly for your writing. When you're writing an equation, equations get their own line and they get their own number. Also, you have to define the variables that you use in your equation in the text. So here's an example from something that I wrote. Again, water vapor transmission rate as a function of time. That's this variable, which I've defined with words, water vapor transmission rate, was calculated as, here's my equation, and it has its number. All right, it has its own line. Where delta M is the mass change of the system, yeah, it's delta M. I'm describing that variable with words. A is the area of the cup, little a, and T is the testing time, T. And you'll see that each one of these variables in the text is italicized, right? So you see this little T is italicized, indicating that it's a variable in the equation. Delta M is italicized, indicating it's a variable in the equation. A is italicized, etc. All right? And I've clearly defined what each one of these variables stands for, and the equation is formatted properly. Right? Last couple things here, and then we'll get you out for the day. My last couple bits of advice, and you will hopefully learn to improve upon these things as this quarter goes, some of these subtle things. Number one is you should be writing in the past tense almost exclusively throughout your document. For sure, you should be in the methods section writing in past tense. For sure in sort of the results section, right? Your methods, what did you do? Past tense. We tested this, okay? This was tested. This was evaluated. Past tense, all right? When you get the results, the stress was blah. The strain was blah. Past tense, right? So that's what I mean right in past tense. Write in strong, declarative, non-passive language. So you might see me criticize your work by saying something like this phrase is in passive voice. And I think even like Microsoft Word kind of now checks for passive voice. And I think it does a pretty good job. But what I mean by passive versus non-passive voice is something like a bad example. Stress can be calculated by dividing the load by the cross-sectional area. Can be is just like passive aggressive. It's like, can you clean out the fridge? It's like, yeah, okay, I could. You want me to? Right? Like, be strong and assertive and say what it is you did. The stress was calculated, rawr, okay, by dividing the load by cross-sectional area. All right, another bad example here. The material may be considered isotropic. Okay, well, did you consider it to be isotropic, or like could it just be so? Right? Okay. The material was assumed to be isotropic. All right, the difference between passive and active declarative language. Right? Stay away from personal pronouns. We calculated the stress to be blah blah blah. That's not the best. All right, so just state what it is you want to state. The stress was blah. All right, you don't need to say we calculated the stress to be this. All right, okay, I know you did the calculation. Like, the stress was X. All right, limit your use of other pronouns. And this is another really big one that happens even at the highest levels. The load on the beam was recorded with a load cell. It bent a lot when the load was applied. What is it? Okay, is it the load cell? I mean, there's three nouns in this sentence: the load cell, the beam, and the load. Okay, when you say it in your next sentence, I don't know what it is. All right, is it the load cell? Is it the beam? You know, like, you gotta be clear. All right. Much more clear is the load on the beam was recorded with a load cell. When loaded, the beam deflected. Okay, there's no ambiguity there. There's no room for a pronoun to be this or this or that. You know, if you've ever like talked to somebody who uses excessive amounts of pronouns, it can be like really hard to follow their stories. Like, if you're hanging out with someone and they're telling you a story about this weekend when they were hanging out with 14 people, and they're all of a sudden like, he said this and she said that and she said this and he said, and you're like, who is he? Who is she? I can't follow your story. I don't know who you're talking about. Okay, like, chill out with the pronouns. Like, use their names. Right? Jared said this and Aaron said that and Billy said this and Christina said that. Okay, it's much more easy to follow the story. It's the same idea here in writing. If you say it did this and this was that, and like, you can't follow that. Like, use the actual thing itself. Like, write it down what it was. All right. Another thing that happens a lot with intermediate and novice writing is people just use way too many words. All right. You're gonna have a 3-page limit on your lab reports, so you gotta like rein it in. All right. Be succinct. This is a little passage I just made up. The yield stress is the region on the stress and strain curve where it starts to flatten out or slowly rise after previously being purely linear, which is the linear elastic portion of the curve. And man, I'm already tired. Okay. You can say what you want to say in much less words, right? Though not present in every material, the yield stress is calculated as the stress at which the linear elastic character of the solid material is lost under incremental loading. Done. Okay? It's very clear and clean. I feel so much better. Okay? All right. Finally, follow other well-established practices, including don't end phrases with prepositions. All right? We loaded the sample up. Yeehaw! All right? Whoop-de-doo. We loaded it up. Let's go. All right. No. All right. Up is a preposition, doesn't belong at the end of a phrase. Right? The sample was loaded. Period. Right? Use adverbs properly. Oh, this drives me crazy when I see this. Fresh squeezed lemonade. Oh, when you're describing how something was squeezed, you need to use an adverb. Freshly. It was like freshly squeezed lemonade. You use an adverb to describe what happened with the verb. Okay, drives me crazy. The beam bent up. Oh, the beam bent vertically. All right, proper adverb. Finally, make sure information goes in the right section. Here's an example of something that someone wrote in a previous class in their results section. And generally this phrase is like pretty nice. The yield stress was calculated using the 0.2% offset yield method. The yield stress was 30 MPa. This is outside the normal yield stress value expected for high-density polyethylene. Great, fantastic. But if that's in the results section, then some of the information that you have written there is misplaced. The first sentence there, the yield stress was calculated using 0.2% offset yield method, is a method, right? That belongs in the method section. Here it's sort of written as part of the results section, which is not accurate. Okay. That second sentence there, the yield stress was 30 MPa, that's good. Okay, that belongs in the results section, and that's perfectly legit. This is outside the normal yield stress value expected for HDPE. Okay, that's a discussion because HDPE has a well-established, modulus or stiffness or strength or etc. And so when you're discussing some abnormalities and something you might have measured, that's sort of a discussion point and belongs in the discussion section. Okay. Finally here, Be particular about your wording and your vocabulary. We measured distress. That looks like a great statement. We measured distress. But you can't actually measure stress. In sort of the tradition, I mean, there are some very strange ways to do it, but you can't really measure stress directly. What you're going to do in this class is measure changes in resistance of strain gauges and then use that strain with Hooke's law to calculate stress. It's a very clear distinction here in that stress is something that is calculated from a measured strain. So you're not actually measuring the stress itself. You have to be careful with your vocabulary. So that's what I'll say about that. The second list of bullets here, the elastic modulus of the epoxy was 2.2 GPa, stronger than most polymers. Okay, when you're talking about elastic modulus is a stiffness, not a strength. So careful with your vocabulary. All right. Figure 4 illustrates the design concept. Okay, well, this is again an object-subject issue. Figure 4 can't illustrate anything. Does it have a pencil in its hand? No. Is it drawing something? No. What you mean to say is the design concept is illustrated in figure 4. You got your object and your subject backwards in your sentence. All right. Okay, so I've done a lot of just introductory material on writing good lab reports. I hope some of it will stick. This is going to be it for today. I'll see if Alan kind of came back at me with his question. It looked as though the reference numbers took the place of quotes completely in the report. Do we not use quotations or just reference the article with the reference number? So I'll show you an example of what it should look like. Maybe that'll clear things up, Alan. So let me get a paper that I've written, and it will be probably very clear once you see this particular paper. All right. So let's do this. Okay. So here's a paper that I've written. You should all be able to see this on your screen. And what you'll notice here is that in the text, you'll see bracketed number, bracketed number, bracketed number behind various statements. Here we have a bracketed series of numbers 3 through 12. So this is how it should appear in the text. Then when I scroll down to the end and I look at the references, the references will look like this, right? Where I have the full information about each one of the particular pieces listed in the numerical order in which they appear, right? And the various referenced material will change how the reference appears at the end of the document. So if you're referencing an ebook, use the ebook guideline for that. If you're referencing a journal article, use the journal article guidelines, etc. Okay? So hopefully that's a little bit more clear. Other questions? Okay, well that's it for today. Thanks for coming, and those of you in the C block, which are kind of the last letters with the end of the alphabet, eligible for a lecture tomorrow. And I worked out my sort of technical issues, so it should be good to go tomorrow. So sorry about that. Hopefully we'll see you there tomorrow. I look forward to seeing some of you guys in